Well, thank you very much for the kind invitation to come here. It's a little bit warmer down here than it is in the east of Scotland right now. So I'm going to be talking about something I've worked on for much of my life, actually. These neurosteroids, which, as you'll see, are very, very powerful modulators of the brain's major inhibitory receptor, the GABAA receptor. So this work started a long time ago, in the 1940s, actually, with a beautiful, simple experiment done by Hancheye. And what he demonstrated was that if you added certain metabolites of progesterone, then quite quickly that animal became anesthetized. And then if you, it also had a magic ability to make it disappear. And then if you put it in fresh water, non-steroid containing water, then the animal recovered. So it was producing a very dramatic effect on the activity of this animal. But it wasn't known how. And it wasn't until actually the 1980s that this is a picture of Mike Simmons of the School of Pharmacy and his then graduate student Neil Harrison were working with a rat brain slice preparation. And what they showed was not these naturally occurring metabolites of progesterone, but a synthetic one at the time that Glaxo had made, which is called alfaxolone, and they were marketing that as an IV anesthetic. And what he found was that alfaxolone at very, very low doses caused this nice enhancement of the GABA response. And it was a highly specific interaction because the 3-butyl isomer, so just changing this hydroxyl, the orientation of this hydroxyl here, was totally inert and wasn't behaviorally active. And they didn't touch related receptors like the strychnine-sensitive glycine receptor. And way back then, that was when I was just setting up my lab, and we were working on how barbiturates and benzodiazepines enhance GABA receptors. But we were drawn by a comment in the discussion where Mike Simmons remembered that other steroids, including endogenous steroid hormones and metabolites, might also interact with the GABA receptors. So we immediately dived into the Sigma catalog. And there are lots of these different metabolites, and chose one or two and found that they are incredibly potent. So this is much later. We weren't using recombinant expressing cDNAs in those days. The GABA receptor hadn't even been cloned. But in this experiment, just to show you how potent these compounds are, we've injected this frog egg sometime earlier with cDNAs encoding for particular human GABAA receptors. And here we're applying a dose of GABA that typically would give a response, 10% of the maximum, and then introduce briefly a very low dose of this compound here, 5-alpha-pregnan, 3-alpha-20-one, also known as allopregnanolone, and mainly I will refer to it as 5-alpha, 3-alpha. And you can see now at 10 nanomolar, you're beginning to get an enhancement of that response. And if you go up to 100 nanomolar, then you get a much bigger effect. And this was interesting because the best estimates, albeit in plasma, of circulating levels of these neurosteroids, these metabolites, at rest around about 3 nanomolar. Remember, this is just plasma, not what's in the brain. And then during acute stress, for example, the levels of these steroids go up to about 30 nanomolar. And an extreme, which I'll be focusing on, is pregnancy, where they can get up to as high as 100 nanomolar. So this receptor is sensitive in the right sort of range to play a physiological role. So at that time, we thought that these steroids were coming from the adrenals and also in women from the ovaries. But a number of groups, particularly in Italy, actually, a group in Milan, showed that certain glial cells and certain neurons have the enzymes required to make these steroids in the brain, and hence the word neurosteroids. So here's the enzymes here. So you could go from peripherally derived progesterone, for example, and then it would be metabolized to produce this GABA active compound, or the cells themselves, all the way from cholesterol, are capable of making these compounds. And they bind specifically to a site on these are the synaptic GABAA receptors. And what they do is they promote the likelihood that the channel stays in the open conformation. And so fast phasic events, as a vesicle of GABA hits these synaptic receptors, you get this inward current, and then it's prolonged. So it's energetically more favorable to stay in the open state for a little bit longer. And then a number of groups identified that in some neurons, there are not only these fast phasic synaptic receptors, which have a low affinity for GABA itself, so they're very transient, but some neurons express these extrasynaptic receptors, which tend to have a much higher affinity for GABA and tend not to desensitize as readily as these. And they form a tonic current, or make a tonic current, and that's either due to spillover of GABA, so they have a really high affinity for GABA, or now, as we're beginning to learn, a number of these receptors are actually spontaneously opening. And when GABA is released at a higher rate, that amplifies that. So as you might expect then, being a GABA modulator, they have anxiolytic effects, antidepressant, which I'll touch on a bit more. They're powerful anticonvulsants. They are sedative, and as shown so long ago with the fish experiment, they are at high doses anesthetic. They're general anesthetics. And more recently, we discovered that not only could certain neurons here or certain glial cells here make these steroids, but actually some neurons are capable of making these steroids in a sort of autocrine fashion, where they can then go, the steroid will go into the membrane, and the binding site for these steroids is located in the transmembrane regions. Okay, so when we started, there was only one GABA receptor. Some brave people suggested to the FISSOC and FARMSOC there might be more than one, and they had a hard time of it. And then the cloning happened in Cambridge. Eric Barnard and Peter Seeberg, they found the first subunits, the alpha 1 and the beta 1, and then quite rapidly they found a whole load more. In fact, you have in your brain something in the order of 19 different subunits, which, if there was no rules governing which of these can come together, and thankfully there is, you have the capacity to make something in the order of about 500,000 different types of GABAA receptor. Thankfully, there are some rules governing this, and estimates vary, but somewhere between 20 to 30 different subtypes exist in human brain. And this is just an autoradiogram with beautiful antibodies by Jean-Marc Fritchie, just showing that these where it's warmer, these yellow and brown represent high density of binding for the different subunits. You can see there's a lot of alpha 1 here, but some of them are quite particular, like here, the alpha 5 decorating the hippocampus, and one that I'm going to be talking about quite a bit are these delta subunits. So over the years, it's become evident that these different receptor subtypes have distinct physiological and pharmacological properties. As you can see, they're not uniformly expressed in the CNS, and they mediate, we now know, different types of behavior. And so the important question, if you're looking at neurosteroids, is which of these receptors is important for mediating those behavioral effects? Okay, so a lot of work, particularly by the Swiss group of Hans Möller and Yu Rudolph, and the Merck, when Merck was in Turlings Park, making mice that carried a point mutation that stopped things binding to them, like the benzodiazepines. We got a picture of some of these different receptor subtypes and what behaviors they mediate. And some of our own work together with Merck was looking at general anesthetics with a point mutation to make them stop binding. And there are different aspects of their behavioral effects that are mediated by different receptors. So what about the steroids then? So it's a bit of a mess for the steroids because this was a painful study by a PhD student in our lab expressing lots and lots of different subtypes looking for selectivity. And the bottom line is that there is little selectivity, although there was interest in this combination here, alpha-4, beta-3, delta. And here you can see the dose response curve for 5-alpha, 3-alpha enhancing GABA here for alpha-4, beta-gamma compared to when it's with the delta. So there is some selectivity, but not a lot. In other words, they're quite promiscuous. They're highly selective for the GABAA receptor, but not selective across different subtypes. So just briefly, just to show what these do then. So here's a recording from brain slice under the conditions shown above. And we're recording the synaptic events here, which, as I say, are mediated by these, a lot more receptors than the ones I've drawn here. But there's a cloud of GABA hits these receptors, activates them. Chloride under these conditions is going out. And you can see this as an inward current. And when you add the steroid then, it prolongs fast phasic neural inhibition. And then regarding these tonic currents, which are mediated by different receptors, so now the trace is slowed up, squashed up. This is a couple of minutes or so, so it just appears as a very noisy trace, and these downward spikes are these phasic events. And then if you hit it with a GABA antagonist like bicuculin, you can see that noise goes away, and it reveals this current, this background current here. And the noise is because the channels are spontaneously opening and closing by themselves. Okay, so these delta receptors have turned out to be really interesting. So they're located perisynaptically or primarily extrasynaptically. They have a different pharmacology. They are not benzodiazepine sensitive. And they change their expression levels under a number of different conditions. So during the estrous cycle, certainly in mice, pregnancy, which again I will focus on postpartum, and their expression is sensitive to stress. And surprisingly, given that promiscuous picture I showed you for the different GABA subtypes, accepting that knockouts have their own issues, here's the delta knockout mouse. And we lose a lot of the sedative effects of the neurosteroids in this. This was done for alfaxalone and also this endogenous steroid pregnenolone. And you lose the anxiolytic, the anxiety-reducing effects of this synthetic steroid here. So it seems as though they play really quite an important role. So now, for the remaining time, I'd like to more focus on what goes on during pregnancy and postpartum. So this is all in mice. So for wild-type mice, these are in dentate gyrus granule cells in the hippocampus. Wild-type mice, the tonic current is mediated by alpha-4 beta-delta. And the synaptic phasic current, which might be alpha-1 and alpha-2 beta-gamma, both of these during pregnancy, their expression is reduced. And then they recover, the receptor expression recovers postpartum. And this altered tonic current is mirrored by changes to delta subunit expression. Now, for delta knockout mice, obviously the tonic current in these neurons is reduced throughout pregnancy and postpartum, but the synaptic phasic current still decreases by day 18 and then recovers postpartum. These postpartum delta knockout mothers are impaired in a number of ways. They're impaired in something called the forced swim test, which is loosely called a depression-like test. They don't show preference for enjoyment, like taking sucrose. And they provide, importantly, very poor maternal care if you observe them and video them and how they're behaving with the pups. So having worked on this since the late 80s, it was very rewarding when Sage Pharmaceutical got FDA approval, not for a synthetic compound, but actually for allopregnanolone itself, which they just put in a particular solvent called brexanolone, also called Zulresso. And that has really sparked or reignited interest in this whole field. So here's what's going on in pregnancy. You have greatly raised levels, as I mentioned at the beginning, of allopregnanolone getting up to, at least in plasma, 100 nanomolar. And that somehow is causing reduced expression of these GABAA receptor subunits, and it's speculated that that's to prevent some of the sedative effects, but to maintain the anxiolytic and also the pain-relieving properties of these steroids. And then what happens postpartum? On the day of delivery, there is an absolutely dramatic decrease in the levels of allopregnanolone. And for most people then, for most women, female mice, they recover their GABAA receptor expression, and they also recover the levels of allopregnanolone. And one of the theories about postpartum depression is that this recovery of GABAA receptor expression and the recovery of the levels of allopregnanolone is compromised. So this is brexanolone, which I say is just allopregnanolone, given a fancy name for patent reasons. And this was a big study, and there have been numerous studies since, where it was given to women. And it's clearly not perfect, because you have to give it by IV infusion over 60 hours. They have to go into hospital, which obviously is not ideal. They have to be very carefully monitored because, as I mentioned right at the beginning, that actually at high doses, these things are anesthetics. And if you read some of the side effects, certainly sedation is one, but in some cases, they've drifted into an unconscious state. So it's clearly not perfect. However, their mood, as assessed by HAM-D scores, was improved, and it's now improved way past 30 days after this type of treatment, and they're modifying the way that they're giving this, so giving it longer, etc. So how that happens and how that stays like that, we don't know. But there are one or two ideas emerging. So it's effective in improving this mood disorder. I should also say it's being looked at by SAGE in particular as a treatment for major depressive disorder. Okay, so our current work is very much with guys in Cardiff who have, we're nearly done, okay. So we have a project which is looking to develop neurosteroids that are useful in treating postpartum depression and also associated things, psychosis. And I've mentioned why you would want to do that. So the aim of it is to develop synthetic, orally available neurosteroids probably with reduced GABA efficacy to try and limit this sedation and improve pharmacokinetics because it's rapidly metabolized. And we also have a project with the same group, funded by the MRC, investigating whether if you made a non-steroid that was selective for these delta receptors, would it be useful? And I'll just briefly show you that. So this is all based on work we did years ago on this compound here called DS2, which is beautifully selective for those tonic currents mediated by the delta subunit. So this is a recording we made from thalamus. We know it's alpha-4 beta-2 delta from various knock-in and knock-out that we'd done. And here you can see as it comes in, that tonic current increases. And then we hit it with bicuculin, and there's the size of that current. But crucially, if you look at the synaptic events, it has absolutely no effect on those. So it's completely different to the steroid. It's highly selective. And various mutagenesis studies show that it seems to have a novel binding site that is distinct from benzodiazepines, from certain anesthetics like etomidate, and also from where the steroids themselves bind. Okay, so to finish then, what we're doing together with Cardiff is they are expressing HEX cells with alpha-4 beta-3 delta, and as a representative of the synaptic population, alpha-1 beta-3 gamma-2, and then screening for selectivity, potency, and EC50. And if something emerges from that that looks interesting, we then use single-cell patching of neurons to look at what they do to the tonic current and make sure that they are or are not doing anything to the phasic current. And then if it gets through all of this, then we inject them into freely moving mice to see what it's doing to the local field potential and how long it's doing it for. I should just add, and then I'm finished, that so this is a workflow that we've established with Cardiff before, and it works really well. So what goes on here is often predictive of what we've found when we go to real neurons. Not as clear for these alpha-4 beta deltas. There's something else which, not surprisingly perhaps, is not captured in a HEX cell compared to these neurons. Okay, so finally then just to thank people in the lab, Steve Martin, who does all the in vivo stuff, Delia Bolelli, and John Peters, who were in with me right at the beginning of all of this. And then this is the group in Cardiff that some of you will know, John Atack, Simon Ward, Michael, who's responsible for the steroid project, Darren for the Delta project, and Owana, who is here somewhere today. Okay, so thank you very much for your attention.
We have time for one or two very short questions.
Thank you, Jeremy. A wonderful romp through neurosteroids and GABAA receptors. That brexanolone effect is really quite striking with the 30-day duration and beyond potentially. So acutely, you assume that you're, boosting the allopregnanolone levels with this acute application.
Yep.
But then those longer lasting effects presumably are even beyond something like, protein expression, as in protein expression would also go beyond or would be less than a 30-day. So it's presumably almost a structural change, whether it be synapse formation or...
So that's the surprising thing, and I think the later data now is more dramatic than that, where they've changed the regime of how it was given and then how long they're following them for over months now. So I don't think that is going to be just a GABA thing. There is a story that it changes expression, of the GABAA receptors, and that's one of the things that we're interested in. But people are looking at other things. So for some reason, after this, inflammatory cytokines are down, and there's some recent work showing that it hits a receptor I don't know very much about called the Toll-4 receptor. And these levels of things, particularly like IL-1 beta, are down for quite a long period of time. So the focus is moving to that non-GABA side of it, actually. But with a synthetic compound like that DS2-like thing, which I forgot to mention, doesn't get in the brain, so that's why we're studying it. We're trying to make one that actually does. That would be useful. But I don't know if you would get that anti-inflammatory effect.
Thank you.
One more question here, and I'm afraid we don't have time for more.
Thank you. Great talk. I was wondering whether you had any thoughts on whether there are different functions or modes of the different endogenous these neuromodulators that you're talking about here, neurosteroids. There are different endogenous neurosteroids like TH-DOC or allopregnanolone. Are there different functional effects of those on the brain?
I think that TH-DOC is more prevalent in the spinal cord, where it has pain-relieving properties, and its levels are greatly increased when you have in the neuroinflammatory models. But as a straight comparison of allo versus the DOC, I'm not aware of any big differences that are coming. Some of the work of Trevor Smart, where he's made a mouse that carries that mutation on the alpha-2, is really interesting because the phenotype of those mice, they have an anxiogenic phenotype. And then when you apply allopregnanolone and inject it, you're not getting those reduced anxiolytic effects. So that, and together with some stuff we did in neural development where the steroid levels are really high and then they drop away over a period of 2 or 3 days, right when eyes are opening, suggests that they do truly play an endogenous role without injecting extra.
Thank you.